Adrian Newey has designed a Formula One car so extreme that rival teams reportedly admitted they would not have dared to attempt it. Its rear suspension appears to reach into territory normally associated with aerodynamic bodywork. Its tiny side pods push the Honda installation toward a dangerous limit. And now, after months of failure, excess weight, and painful silence from Aston Martin, Newey is bringing a heavily evolved version to Hungary. A new nose, substantially revised aerodynamic surfaces, a lighter chassis, a lighter gearbox, a revised rear suspension, and structural changes significant enough to require fresh crash testing. But the governing body is not shaking, and there is no confirmed ban, penalty, or formal protest against the car. The truth is more interesting. Because the evolved AMR26 is forcing Formula One to confront a question that has followed Adrian Newey throughout his career. When does a mechanical component stop being only mechanical and begin behaving like an aerodynamic weapon? The answer could influence far more than Aston Martin's season. Subscribe to the channel. The controversy began before the AMR26 had completed a proper race weekend. Aston Martin revealed the car during a shakedown in Barcelona, with Lance Stroll behind the wheel. Almost immediately, attention moved toward the rear. Not the rear wing itself. Not the diffuser. The suspension. The geometry appeared unusually aggressive. One of the rear wishbone elements was attached near the rear wing support in a position that visually reminded observers of the beam wing, a separate aerodynamic device that had been removed under the new regulations. That did not automatically make the design illegal. Suspension components are allowed to exist for clear mechanical reasons. They must control the wheels, support the car, and manage the forces created during braking, acceleration, and cornering. But every Formula One engineer understands something important. Anything exposed to the air can influence the air. A suspension arm may have a mechanical purpose, but its shape and position can also guide airflow. That creates a difficult boundary. The rules may define what a component is supposed to do. The air does not care what the rulebook calls it. Air only reacts to shape, angle, speed, and pressure. Imagine placing a long spoon beneath a running tap. You may claim the spoon is there to hold something, but the water still bends around it. The purpose you describe does not change the physical effect. That is why Newey's rear suspension created such immediate interest. If the component genuinely exists to control the rear wheel, it can still influence the airflow around the back of the car. And if its placement helps organize that airflow in an area where other aerodynamic devices are restricted, the design becomes extremely valuable. This is where the story becomes complicated. There is no confirmed ruling declaring the suspension illegal. There is no confirmed technical directive aimed specifically at Aston Martin. There is no confirmed formal protest from a rival team. Reports indicated that the governing body examined whether the car's structures met the required safety standards, but no public source confirmed a ban or disqualification. So the real controversy is not that Aston Martin was caught breaking a rule. It is that Newey appears to have explored the space between the wording of the regulations and the behavior of the air. That space has defined some of the greatest engineering battles in Formula One history. The rules describe boxes. Designers search for the gaps between those boxes. A regulation may restrict a wing, so engineers look for another legal surface that can perform part of the same job. A rule may control flexibility, so teams design structures that remain strong during testing but respond differently under real aerodynamic loads. A device may be banned by name, but the airflow effect that made it valuable may still be possible through another component. That does not mean every clever interpretation is accepted. The governing body can clarify the rules. It can change testing procedures. It can issue technical guidance. It can close a loophole if the design moves too far away from the intention of the regulations. But until that happens, the design exists in the most valuable territory in Formula One, the edge. And Adrian Newey has spent decades working there. Yet the first version of the AMR26 did not become a dominant machine. It became one of the slowest cars on the grid. That contradiction is the key to everything happening now. How could a car with such radical ideas, created under the leadership of the most decorated designer in the sport, fall so far behind? The simple answer would be that the concept failed. The real answer is deeper. Aston Martin started the project late. Newey admitted that serious work on the 2026 car did not begin until the middle of March in 2025. The first model entered the wind tunnel in the middle of April. By that stage, rival teams had already spent months studying the regulations, building concepts, rejecting weak ideas, and improving stronger ones. Formula One development is not one act of inspiration. It is repetition. An engineer creates a shape. The simulation suggests a gain. The wind tunnel exposes a weakness. The shape changes. That new shape affects another part of the car. The entire system must be tested again. A team may repeat that process hundreds of times before the first race. Starting late does not only mean having fewer days. It means completing fewer cycles of learning. Imagine trying to solve a difficult puzzle while another person has already tested half of the possible combinations. You may be more creative. You may eventually discover a better solution. But the other person has already eliminated many mistakes. Aston Martin was still finding those mistakes while its rivals were refining their answers. And when time disappears, weight usually appears. Newey said the original chassis was well above the minimum weight. That happened partly because the team did not have enough time to optimize every component. When engineers can work carefully, they remove material from areas where it is not needed. They test the part. They study the stress. They strengthen only the sections carrying the greatest loads. The final component becomes lighter without losing safety. When engineers work under intense time pressure, they often choose security. A thicker section. More reinforcement. A larger safety margin. The part is ready sooner, but the car pays for it on every lap. Extra weight damages acceleration. It increases braking distance. It makes direction changes more difficult. It places more energy through the tires. It also prevents the team from using ballast effectively. Ballast is not useless weight. It is carefully positioned mass that engineers can place where it improves the balance of the car. But when the basic structure is already too heavy, that freedom disappears. The team carries weight where the rush design left it, not where the driver needs it. Think of wearing a backpack filled in a hurry. One heavy object sits far from your back. Another slides from side to side. The total load is only part of the problem. The position of that load makes every movement more difficult. The original AMR26 carried that type of compromise. But excess weight was not its only enemy. The new Honda power unit created serious integration problems. Aston Martin had moved away from being a customer of Mercedes and entered a dedicated partnership with Honda. That should create a major long-term advantage. A customer team receives a power unit that must work within another manufacturer's broader program. A factory partnership allows the chassis and engine groups to design around each other. Cooling requests can be discussed earlier. The bodywork can be shaped around the engine. The gearbox and rear suspension can be developed as part of one package. In theory, everything becomes more efficient. But theory is not reality. The Honda installation reportedly suffered from cooling difficulties, gearbox heating, battery system problems, and vibration. Former driver Ralf Schumacher described the beginning of the partnership as a major disaster. That language was severe, but the results made the frustration understandable. A Formula One power unit is not one independent object. It is connected to almost every major system in the rear of the car. Cooling affects the side pods. The side pods affect the airflow. The airflow affects the floor. The floor affects the rear suspension. The rear suspension affects how the car holds its aerodynamic platform. One compromise spreads into another. And Newey's aggressive packaging made the situation even more difficult. The AMR26 used extremely small side pods. That created the potential for cleaner airflow around the body of the car. Smaller bodywork can give engineers more freedom to guide air toward the floor and rear surfaces. But small side pods leave less room for cooling. The power unit still creates heat. The battery still creates heat. The gearbox still creates heat. That energy must escape. Imagine placing a powerful computer inside a tiny sealed cabinet. The smaller cabinet may look cleaner and occupy less space. But the machine inside still needs air. Without enough cooling, performance drops and reliability suffers. Aston Martin appears to have pushed that balance too far in the first version. The packaging was ambitious. The cooling capacity was not ready. The idea that should have improved aerodynamic efficiency began suffocating the mechanical systems inside the car. This created a painful cycle. The car developed problems during testing. Those problems reduced running. Reduced running meant less information. Less information made it harder to understand the aerodynamics. The team could not separate one weakness from another. Was the car slow because it lacked downforce? Was it slow because it carried too much weight? Was the balance unstable because the floor was inconsistent? Was the floor being blamed for behavior caused by vibration? Was the Honda installation limiting the bodywork? Or were the aerodynamic surfaces making cooling harder? When multiple problems arrive together, each one can disguise the next. A team changes the bodywork, then discovers the real issue is structural movement. It changes the setup, then learns the tires were reacting to excess weight. It adds cooling, then loses aerodynamic performance. Every solution creates another compromise. By the opening races, Aston Martin was not fighting near the front. Reports suggested the team might even struggle with the qualifying threshold that requires a car to remain within 107% of the fastest time in the first qualifying session. The project that had been presented as a future championship challenge was facing embarrassment. And yet, Aston Martin did something unusual. It did not respond with a constant stream of small upgrades. Newey chose to wait. He described that decision as painful. While rival teams improved their cars from race to race, Aston Martin continued using a package it already knew was not good enough. From the outside, that looked passive. Inside the team, it may have been the only rational choice. Small upgrades can help a healthy car. But when the basic platform has several connected weaknesses, small parts may only create more confusion. A new wing may add downforce, but the overweight chassis still hurts the tires. A revised floor may improve one condition, but poor simulation tools may make the result difficult to predict. New bodywork may improve cooling, but damage the airflow path Newey wants for the future. Instead of spending resources on temporary corrections, Aston Martin stored its development effort for one larger package. That package is the evolved AMR26 arriving in Hungary. And it does not abandon the original aerodynamic philosophy. That is important. This is not Newey admitting that the entire concept was wrong and replacing it with a completely different car. The central approach remains. The evolved package is designed to attack two major weaknesses: insufficient downforce and excessive weight. But the changes required to address those weaknesses are much deeper than a normal race upgrade. The front suspension remains unchanged. The rear suspension is slightly revised. The car receives a new nose. Its aerodynamic surfaces are substantially different. Weight has been removed from the chassis and gearbox.